So a GANT is made of two adversarial networks, a discriminator and a generator. We know that the generator is going to take in some latent vector z and output some pixel values. And our discriminator will alternate between training on the output of our generator and on a sample from our MNIST training data. This is going to be a pretty typical linear classifier that aims to classify these images as either real or fake. So in both cases, it should see some input pixel values. And for a linear model, you need to make sure that these are flattened, if need be, into a vector shape. So a 28 by 28 image should be a vector of length 784. Then it takes a flattened input and passes those through at least one hidden layer. I'd recommend using at least a couple hidden layers. And these hidden layers should have one key attribute. They have a leaky ReLU activation function applied to their outputs. A leaky ReLU is very similar to a normal ReLU, in that it takes in some value and will leave that value alone if it's a positive value. But if that value is negative, a normal ReLU would have set it to exactly 0. But a leaky ReLU will actually multiply this value by some small constant called the slope. In fact, let's click on this documentation to learn more. Here we can see that the leaky ReLU activation function takes in a parameter negative slope. And this is the value that it will multiply any negative inputs by. The idea is that this allows for more nuance in recording gradient calculations during backpropagation. Instead of looking at a 0 gradient, we have some variance for negative values. Okay, so after a couple leaky ReLU activated hidden layers, there will be a final fully connected layer. This layer will be responsible for generating one value, a class score between 0 and 1 for fake or real. And we can get this value by applying a sigmoid activation function to the final output layer. Alternatively, we could apply the sigmoid activation function later when we calculate the loss, and leave this layer alone without an activation function, which is actually what I recommend in this case. And you can read a little bit more about applying a sigmoid in the loss function here. Okay, so your first task will be to define this discriminator. And here's the starting class code. This should take in an input size, which should be our number of flattened pixels in an input image. And it takes in a hidden dimension, which should be the output size of our final hidden layer. And finally, an output size, which specifies how many outputs you want this model to produce. Now, if you have more than one hidden layer, you can use this hidden dimension and just multiply it by factors of 2, scaling it until your final hidden layer has this number of hidden outputs. Your next task will be to define the generator. The generator network will be very similar to the discriminator, except for a few main differences. We want this to take in a latent vector z, which will be of some size that we specify. This vector should actually be upsampled as it goes through hidden layers until we get to a last layer that can be reshaped into a new fake image. The hidden layers should have leaky ReLUs applied, and the last layer will have a tanh activation applied to its outputs. And this is just due to the existing literature. The generator has been found to perform the best with a tanh activated output layer. Now the tanh activation function scales any value to be between 1 and negative 1, as opposed to 0 and 1 like a sigmoid. And you can see that in this function here. Recall that we also want these outputs to be comparable to the real input pixel values, which are read in as normalized values between 0 and 1. So later, when we train the discriminator, we'll also have to scale our real training images to have pixel values between negative 1 and 1. And I'll do this in the training loop a bit further down in the notebook. Now try to complete the discriminator and generator classes on your own. If you're confident in your model definitions, I encourage you to continue in this exercise notebook and instantiate the networks with some specified hyperparameters. As usual, if you're stuck or want to check your work, next I'll go over one solution.